Hello and welcome to PyData Global 2021. My name is Kevin. I am very, very happy and excited to be here and to be your host for this session. I would like to welcome Karishma, Babbar and Kalyan Munjuluri to our session. I'm just gonna head over to you guys. So please welcome.
Thank you, Kevin, for this warm welcome at PyData. Good morning, good afternoon, everybody. Thank you for coming in. This is our first time speaking at PyData Global. And Kalyan and I are really excited to spend the next 90 minutes or so with you all talking about the life cycle of machine learning projects, challenges involved, and how MLflow can be leveraged to address those challenges, followed by a code-along session. So without further ado, let's get started. Here is an outline of the session. We begin by discussing the typical life cycle of a machine learning project, followed by the development challenges encountered at each stage of the life cycle. We will then introduce MLflow, its components, and address how it solves the development challenges stated earlier. We will be spending majority part of this session implementing each component of MLflow for 2 examples. The notebook used in this session will be shared in a short while. And we would be happy to take any questions you may have at the end of each topic. We would close today's session with a recap of the tutorial and a takeaway exercise. Creating machine learning solutions to various problems can be quite the arduous task. Until recently, all of us were learning about software development life cycle and how it goes from requirement gathering to designing to development, testing, deployment, and all the way down to maintenance. We were and still are studying the waterfall model, iterative model, and agile models of software development. Now we are at a stage where we want to leverage more from the incoming data by means of machine learning. This new requirement transforms some principles of software development lifecycle to give way for machine learning lifecycle. Beyond the usual concern in software development, machine learning development comes with its own additional challenges. The usual process for building an end-to-end machine learning project involves collecting and processing raw data, analyzing it, featureization steps, training different algorithms, evaluating them, and deploying the best model on some platform for user access. It seems fairly straightforward, right? But in reality, it is not. There are several complexities that arise along the way due to the circular nature of this process. Everyone who has tried out machine learning in some form or the other knows that there are multiple tools and frameworks at our disposal for each stage of the ML lifecycle, whether for preparing data, training models, or deploying them in production. For instance, data can be sourced from multiple storage units, including but not limited to Amazon S3 buckets, DynamoDB, Azure Blob storage, and traditional SQL databases. This raw data would then be analyzed, cleaned, and processed using sklearn, pandas, NumPy, Spark modules from Python. Depending upon the problem at hand, we may either build countless regression or classification models for contextual, visual, or tabular data. Finally, we would deploy these models either in Docker containers or hosted as a Flask web application. As much as it is a bane for us developers to experiment with multiple state-of-the-art ML libraries and frameworks to get optimum performance, it is a bane as it poses multiple challenges in tracking these experiments, reproducing the same results from the same code, and productionizing dozens of libraries. For instance, when we want to experiment with several algorithms, our go-to strategy for tracking the hyperparameters, results, and evaluation metrics for each of these algorithms looks something like this, right? And I hope you all know it is absolutely necessary to use the word final, right? Otherwise, who are we? We are not developers, right? The continuous nature of ML development lifecycle requires constant tracking mechanisms to facilitate comparison and reproduction of results. However, ML is not just code. It is code plus data that we need to keep a track of. But that's not where the story ends. If you thought building machine learning models was difficult. Putting them into production is harder. We often rewrite our code before moving a model to production. This is not only time consuming, but also risky, as it can introduce new bugs and can lead to data drift, concept drift, and infrastructure changes that eventually result in model degradation over time, which is absolutely normal. In some cases, either the model is retrained fully, that takes a lot of time and effort, or a new model is developed to cater to the evolving data, and the unending cycle begins again. Take raw data, analyze it, train a model, deploy it. In a nutshell, if something changes, everything changes. Not to forget the three building blocks of model maintenance in production: scale, monitor, and governance. While code is carefully developed in a controlled development environment, data comes from the unending entropy source known as the real world. Thus, it is absolutely crucial to scale the model to handle large volumes of incoming data, monitor model behavior to detect bias, drift, or degradation over time. Model governance is another important aspect where everything starting from experimentation to deployment is tracked for auditing purposes, where models are tested for speed, accuracy, drift, while in production to avoid inaccuracy. This summarizes MLOps. It's a relatively new and exciting discipline that operationalizes machine learning models from experimentation to production with tools and frameworks that are rapidly evolving. If this does not convince you that MLOps is equally, if not more important than ML development, maybe Elon Musk can. Now, enough about the challenges. Let's dive into standardizing the machine learning lifecycle with an open source solution. MLflow was developed by Databricks, and they released its alpha version in June 2018. It is inspired by existing customized ML platforms from Facebook, Uber, and Google, with a major distinction. MLflow is open source, whereas the former are only limited to their parent organizations. MLflow is compatible with numerous libraries, algorithms, development tools, and frameworks of Python, as well as R. Its modular API-first approach allows you to easily integrate it with your existing ML code base without any significant code changes. It is designed to be platform and tool agnostic, thereby ensuring maximum flexibility for us developers. Today, MLflow is compatible with numerous frameworks, including but not limited to TensorFlow, PyTorch, Keras, Apache Spark, Scikit-learn, Docker, Kubernetes, Amazon SageMaker, Google Cloud Platform, Azure Machine Learning, and Conda. MLflow framework is utilized and contributed to by organizations such as Microsoft, RStudio, Facebook, Booking.com, and many other from the open source community as well. So feel free to read more about these contributors and their work on the official site of MLflow, that is mlflow.org. There are three key components available in the open source MLflow version. These are MLflow tracking, MLflow models, and MLflow projects. MLflow tracking provides an API and user interface capabilities to ease bookkeeping and visualization of experiment runs and results across different frameworks. The second component, MLflow models, facilitates model serving onto a deployment tool of your choice. Last but not the least, MLflow projects allows model packaging in a reproducible manner for cloud as well as local platforms. Let us circle back to how each of these components address the development challenges we discussed earlier. Beginning with raw data. Data for a machine learning model can be in any form of text or CSV files that can be processed either in batches or as streaming data. MLflow tracking API allows the user to log various data files used to train or test a model. Additionally, tracking API can also record the steps followed in the data preparation stage of ML lifecycle. That includes data pre-processing, such as cleaning data, missing value imputation, followed by feature selection and engineering, and lastly, data transformation to make it model ready. Lastly, MLflow tracking does what it promises. It helps you track various experiments with numerous algorithms, hyperparameter tuning, model comparison, and evaluation metrics. One component, MLflow tracking, that covers 3 stages of the life cycle. That's pretty neat, right? So once we have retrieved our data, processed it, fed it into a model, we are ready to serve this model in production. And this is a tricky task, integrating a model with a deployment tool. And it's the primary avenue where majority of machine learning projects fail and not make it into production. MLflow models come to rescue here by packaging models into different formats, also known as flavors. And these will be discussed in more detail in the coming slides. In the end, MLflow projects ties everything neatly together by facilitating reproducibility and reusability of the packaged model for local and cloud execution. Going deep into MLflow tracking. Here are some key concepts that we want to introduce before moving forward. We have been referring to developing machine learning models as experiments. An experiment can be broken down into multiple runs where each run basically denotes execution of a piece of code that gets logged in local files, databases, or remote tracking servers. Code is versioned while it is running from a Git repository. It is important to, overcome the file naming problem that we just discussed earlier, final, finally, and so on. The tracking API also helps you log the project name or the source, input arguments, parameters the model accepts, record evaluation metrics of the model, such as recall, precision, RMSE scores, and so on. Furthermore, this API helps you track artifacts. And artifacts are basically files of any format. They could be your visualization plots, ROC AUC curve, sklearn, pickled models, data files, and so on. Here we depict the tracking API in a simple schematic. We can run notebooks.py scripts, GitHub repos directly through the tracking API and record all associated run details such as metrics, artifacts, and visualize it in the tracking user interface. Now, there are multiple ways to determine where and how we can record MLflow runs. These can be recorded into local files or to a SQLite database or a remote tracking server. MLflow artifacts comprise of local files, and a variety can be imported to a variety of remote file storage solutions. For storing runs and artifacts, MLflow basically uses 2 components for storage. One is known as the backend store, and the other is known as the artifact store. While the backend store contains MLflow entities, such as the run details, the run ID, the name of the source of the run, parameters, metrics, tags, notes, and other metadata, whereas the artifact store contains artifacts such as pickled models or data files, images, in-memory objects, or model summary, and so on. So anything we can think of can be dumped as an artifact, which can later be used to reproduce the run. The MLflow client can interface with a variety of backend and artifact storage configurations, starting with scenario 1. This is the default approach where the runs related artifacts are logged on your local machine. So this is the ideal approach for standalone development scenarios. The second case builds on the default setup and stores artifacts on your local machine, while experiment run details are logged on a SQLite database hosted on your local machine as well. Scenario 3 and 4 incorporate a remote tracking server with which MLflow communicates using REST request calls at the default port of 5000. In scenario 3, we have a tracking UI hosted on a remote server with artifact and experiment run logging maintained on your local machine. On the other hand, in scenario 4, we interface with a SQL database to log experiment runs, and an AWS S3 bucket is used for storing the artifacts. These scenario 3 and scenario 4, these 2 configurations are best suited for collaborative development environments. Here we have a little snippet of code which shows how tracking can be used with your usual ML code. In the beginning, we started on by logging it with certain hyperparameter values. In the middle, we trained the algorithm as we usually do. And last, we log the model evaluation scores of RMSE and R-square. Ultimately, the trained model is also being logged in the end. Coming to the next component of MLflow, that is MLflow models. The need for MLflow models is to provide a streamlined channel to deploy and host various PyTorch, Keras, XGBoost, Spark models on diverse deployment tools such as inference code on Docker, batch and streaming workflows with Spark, and existing ML serving tools such as AWS SageMaker and Azure Machine Learning. There can be n different permutations and combinations between the frameworks that a developer may use to build a pipeline and available deployment tools, which is not very sustainable in nature, right? So MLflow Models API provides a generic framework to serve models in different formats, also known as flavors. These flavors can be a Python function or an sklearn function, Spark function, and so on. The flavors the model is available in is listed in an ML model descriptor file. Each MLflow model is saved as a directory containing a ML model descriptor file that outlines the flavor in which the model can be used. For instance, any model that supports the Python function flavor can be deployed to Docker-based REST server, to cloud platforms such as Azure Machine Learning or Amazon SageMaker, and as a user-defined function in Apache Spark for batch or stream processing of the data. So here we have some concepts involved in this component, including flavors that are formats, modules, or frameworks that are interpreted by the deployment tools, making it easier for these tools to understand the code without the need of any separate integration mechanism. A model signature is a representative of the model schema, such as model's input and output parameters. Additionally, an input example is, as the name suggests, example of the input the model expects. And finally, a YAML file serving as a ML model descriptor file, which outlines these flavors the model is available in model signature as well as the input example. Here we have a schematic of MLflow models and its functionality that is platform agnostic. So this YAML file can be deployed onto a Docker container or in cloud machine learning platforms or as a Flask web app. The last component is MLflow projects that packages models in a standard format for reproducibility and reusability. Like MLflow models, MLflow projects also uses a descriptor file to outline code environment. That is, either we are using a Docker environment or a Conda or a local environment. The model entry point, also known as the main function, with parameters to execute the project, and of course, not to forget the project name. The descriptor file here again is in YAML format. We have a simple schematic here again to represent the working of MLflow projects component. Next, we have a sample MLflow project file for your reference. We have the name, the Conda environment, which is basically stored in the conda.yaml file, which can be referenced by this MLflow project descriptor file. And now we are mentioning the entry point. So our main function will be used to execute our model. The model expects some input parameters, alpha in this case, where we have mentioned the data type and the default value for alpha. And finally, we have the command which would be used to reproduce this run. Now, time for some action. Some code along exercise. But before we get into actual coding exercises, let's get started with MLflow, the installation. So these are the prerequisites. I hope everyone has Python installed on their machines. It can either be a Conda distribution or it can be Python standalone. We would be doing majority of the exercises in the notebook, so it would be wonderful if you have Jupyter notebooks installed. If not, you can do pip install Jupyter and the other modules that we are using, such as scikit-learn, pandas, matplotlib, and numpy. And finally, please don't forget to install MLflow. So you can just do pip install MLflow in your terminal, and we'll be good to start. So here we will take any questions you may have at this point in the basic concepts before we move on to the coding exercises. If there are no questions, we can. Yes, Kevin.
No. I was going to ask if anyone has any question or any.
I think there's one asking for the link for the notebooks. So that's the short URL that you see on your screen. I can also put it in the chat.
Yeah, that's very helpful.
Great. If there are no other questions, we can opt for a 5-minute break. And once we are back, we'll resume the code along sessions. Great. Let's try to be back in 5 minutes. Thank you. So one thing I particularly noticed was when I transitioned from academia to industry, I realized what we learn in academia is more along the lines of how we can develop machine learning algorithms and how we can implement them. But we don't actually pay a lot of attention to how we operationalize them, right? Take them from an experiment stage to production. So that's the background as to why we came up with this topic and why we wanted to introduce everyone to this. So even when we are doing our side projects, it's very useful to have knowledge of all these concepts as to how we can go from procuring the data to developing our models and eventually deploy them so they can drive business value.
Hi, can you hear me? I would have a question regarding the pipeline.
Sure, we can hear you. Go ahead.
Okay, so my question would be, because you asked before about writing your own pipeline from scratch and deploying it. So we've been doing that, and the thing that struck me was that it's always pretty straightforward to write a pipeline for classic applications where you have, I don't know, a classifier or segmentation network, but it becomes really hard to integrate things that are a bit more exotic, like image-to-image translation with GANs, for example. Does MLflow handle those things as well, or is this outside of the scope?
Yeah, no, absolutely. So TensorFlow and Keras, PyTorch, these are all they are all very much compatible with MLflow, and the main problem that we experience with actually applying deep learning concepts is interpretability, right? How we are going through and how we are recording and tracking all of these experiments is usually dependent upon the print statements, right? In this, you can you can save the entire model, you can log all the metrics of each and every epoch, and you can reproduce them. That's the most important thing, right? If I develop something and it's not reproducible later on, then it doesn't necessarily help us deploy that, right? It's not the eventual goal here. So it's absolutely compatible with MLflow.
Oh, that's great. Yeah, for us, mainly the problems are always when it's not like, for example, in training is where the most problems actually arise, is because if you have a classic workflow, you just have your input and the label. But if you have some more complex model, then you may have a bunch of different inputs, or you have a bunch of different outputs, and orchestrating all of that is a bit tricky.
Absolutely, and not just orchestrating, but once you have developed that pipeline, maybe it's very much reusable across your organization. So logging that model in ML tracking with the various configurations that we just discussed, it would be very useful to just distribute the code as well. So it would be a lot less tedious to maintain different models rather than just maintaining one and making more changes into it and logging it as a new model. So there would be versioning as well that you can leverage here.
Awesome, thank you.
Thank you for your question.
Audible?
Yes, Srijit.
Yeah, I had one question. When you said that it is reproducible, so does it log the format of the data or the state of the data in which those accuracies or maybe key values, matrices have been achieved in order to reproduce?
Absolutely. So those can be called as artifacts. So artifacts can be any files you want to log. It could be the data on which you trained.
Thank you.
Great. Thank you for your question.
Maybe a quick follow-up on that question. So if you say the data is also logged, how does it handle deduplication in that case? Because that is kind of the most important part when it comes to versioning data, because you typically have large files. You don't want to have them several times if it's not necessary. Can you maybe talk to that a bit?
So yeah, of course. So I understand it. We could be dealing with some data that's sometimes in GBs, right? 1 GB or 2 GB. So logging that file again and again, it can be rewritten, right? So the initial you can probably log the initial data, and then as you go through the feature engineering steps or the data pre-processing steps, you can log that file again and again. So the same artifact gets overwritten. That's one way you can take care of that scenario in case you don't want to log it multiple times. So in a collaborative environment, we would always recommend configuration 3 and 4. If we can go back to that slide, Kalyan. Great, thank you. So in this case, we could have a remote tracking server where we can visualize everything that we have logged, the ML experiments, the artifacts, and the run details. These two scenarios are most suited for a collaborative development environment, such as that of an organization or multiple developers as well, right? So you can set up a separate tracking server. That server can be hosted in AWS, for example, if not any other machine. It could also be in a Docker container. That totally depends on the use case and how we want to use it, and the developer's preference. Then we can log all the artifacts in an S3 bucket so they can be reused again and again. And storage is not a very big problem when we are storing it in an S3 bucket. And later on, the experiment details, such as I am running an experiment, I am training my model on one data file. I can log those metrics, such as what is my lost error, what are my evaluation metrics, and everything into a SQL database. So either we can go with data versioning of the same file again and again, or we can follow scenario 3 or 4, where I would say 4 in this case when we have big files. So integrating MLflow functionality with cloud and remote servers would be really useful.
Thank you.
So basically, one last question. I think we are reaching the time.
Of course.
MLflow is having its own data versioning control, or we can use DVC along with it. Another open source DVC for data versioning control. So MLflow has its own DVC, right?
Yeah. It does. It helps you do that automatically, but in case you're interested, you can try the integration. We haven't yet though.
Okay.
But we in all our use cases, we feel that MLflow itself, the functionalities that we have inbuilt with MLflow, they are more than enough.
Got it.
Cool.
Great. So over to Kalyan for the code along sessions.
Thank you. Right. So I hope all of you have been able to download a folder that basically contains a few set of notebooks and some data that is where we're working with some model building. So we'll start with the hello world, just to test out whether our installations have been successful and whether we have all the required libraries to basically go ahead. So I'll keep an eye on the chat as well, or if you have any question to ask, feel free to unmute yourself and go ahead. Cool. So Okay, the first one is pretty basic. We're just importing and checking what all versions we have. You might have some slightly updated ones, but that's completely fine as long as this statement is working fine. Right. So help on MLflow would basically give you all the classes, their methods, and so on, right? So coming back to the question where we had something on deep learning, right? So MLflow by default supports TensorFlow, PyTorch, and Keras. So basically lets you whatever model building or experimentation that you do to export it into a compatible flavor that you can, either reproduce in someone else's system or for your deployment approach options that you take. In addition to that, we also have very basic, very common machine learning ones like LightGBM, we have scikit-learn, we have XGBoost, and so on. Just wanted to highlight that. No, for the demo, we don't need anything of any deep learning frameworks installed. We are just working with scikit-learn. So the idea was to keep it introductory and basic so that everyone could follow along. But at the end, we would also leave you some resources that you could explore to have a more advanced model developed. Cool. Yes, that's true. These are supported libraries and models. Cool. Thanks, Karishma. Okay, so what we are doing here is basically defining a function and basically calling some methods within MLflow. So for time being, we'll just leave it as we are setting a name for experiment hello world. We'll dive in deep into what each of these are in the coming notebooks. So you define basically a name for your experiment. And then you use the with. Using the with command, you basically call the start run method. That means from here on, every execution that you do, these can be tracked or logged, and then later on visualized using the tracking UI. So for tracking purposes, we have certain methods like you can set tags, you can log parameters, you can log metrics. Here, we are just putting in some dummy variables for time being just to see everything's working. And let's execute that. And we're also trying to create a directory where we'll see how we can use these directories to basically log artifacts, right? Some of the data that we've pre-processed or some plots that we want to later on visualize after we finished our experimentation purposes. And then we stop everything with an end run command. And then we're just calling the same function above. So it would return a run ID. So these are unique to each run that you do. So an experiment can have several runs, right? You can do as much experimentation as you want in a single experiment that you defined in Hello World. And each of those instances of experiment will have a unique run, and that is basically denoted by the run ID. So runs can also be given a name similar to how we have given a name for an experiment. And that is basically done by passing in an argument within the start run method, right? So if you see, it'll take in a parameter called run name, where you can uniquely name your runs to basically keep them distinct across a given experiment, right? So just to check if we have the entire MLflow setup working properly, I'll just basically navigate to the location where I have my notebooks, right? So this is the location where I have my notebooks. You can also, if you're working on Linux machines, you can use a similar command. And for Windows, you can also use a change dir command. I hope the text on the screen is visible. If not, I can zoom in.
Yeah, now it's visible properly.
Okay. Right. To basically kick off the MLflow UI, it basically starts off at a default port called 5000. And if you have that port empty, then it should work, right? But if, let's say, you want to open it up in a different port, you can do -- port and give a number, the port number with which you want to open it up. right? That should have worked. Now, if I just go localhost and open the particular port, 990, okay. Right, so these are all what we were running, right? An experiment named Hello World. You might be seeing some more because these were all what I was trying earlier, but that's okay. You should ideally see Hello World here in the experiment section. Once you click on that, you should see all the runs within that, right? And if you have provided something with a unique name, you should see the run name alongside. So that's basically a check that your UI is working. I'll take a pause here if anyone's facing any issues or opening up the UI or anything. Okay, looks like we're all good. Cool. We can close this notebook. Yeah, we'll now actually begin with the regression example. Okay. Do you have, so Yang, if you have Conda installed, can you try installing with Conda, the MLflow library, or can you exactly mention which module, for which module you're actually getting that error? So, okay, can quickly share this. So we'll actually go one by one. We'll start with what's the command to change the port. Right. So you can either give -p and give the port number, or you can say --port and give the port number. I hope that answers the port question. Okay, looks like we already found a fix for the module not found error. So, and it looks like creating a new virtual environment should fix it. So Yang, can you try replicating that and let us know if that works? Okay, you cannot access localhost. So if you can't access localhost, you should see the local IP address for your machine. Can you try doing that? Like here, for example, mine is 127.0.0.1 with the colon and the port number. Okay, so before you kick off MLflow UI, you have to make sure that you're in the exact directory where your notebooks are. Because what MLflow would actually do is basically create this folder called ML runs, and and whenever you start off the tracking server, it'll look for a folder called ML runs, which will basically have the experiment IDs within which there'll be run IDs within which. So all of these are basically what consolidates to the UI basically. So can you just retry running the command on the current working folder so that and start off the UI from there? We'll just wait for another minute just to make sure everyone's on the same page. No, you don't have to be on the ML runs folder. You have to be on the folder that's on top of ML runs. So you can basically call the MLflow UI from PyData folder. It's Karishma, can you help with the command for Windows, like change CD? I think it should be very similar. CD, yeah. And then CD, and then path to wherever the downloaded folder is in your machine.
In case your folder structure has spaces, it would be recommended to use the entire folder, the folder name or the path in double quotes. Yeah, in case it has spaces or any other special characters. So that's how you can navigate from the, I only see Hello World and default, and yeah, that's
totally fine. Perfect. So you won't see the rest of the ones because we haven't actually executed the code, but after this session, you should see most of them.
Okay, so can we partly follow and partly on a demo? Because I have lots of people.
Yeah, so that's good. Totally. That's actually, yeah, that's totally fine. So if you, are having some trouble, we will actually hand over these notebooks. You can actually replicate them. But in the interest of time, we'll actually move on now. That's okay. Now fill your code resides. Which folder is that? So it's the same folder that you downloaded, right? Which basically has the notebooks that you just downloaded from this link from short URL.
From short URL, the folder you have downloaded. Navigate to that folder. In that folder, open Jupyter Notebook so that when you see the home screen for Jupyter Notebook, you'll be able to see the data folder where the data sets are stored and the notebooks in that same directory. So when you run the notebook, the Hello World notebook, the ML runs folder will also be created in this downloaded folder. So all your data sets, your primary notebooks that we are working on, Hello World or regression or classification, followed by ML runs. All these 4 items would be there in the same downloaded folder.
So can you tell us, Tom, like what's the exact error that you're facing after Jupyter prompt? Yes, Rishika, I can show you my command prompt.
Okay, this command prompt is not MLflow command prompt. It's normal command prompt. It can be your Anaconda prompt or it can be your simple terminal. Okay, so this is a simple terminal that we open. In that, you navigate to the folder where you have all the notebooks and the ML run directory. And from there, you open MLflow UI. So MLflow UI by default, as Kalyan mentioned, renders the ML runs, everything that's stored in ML runs directory. So if you want, you can navigate to your ML runs folder also, navigate manually outside of CLI and view all the runs for Hello World that you have run. If you've run it only once, only one experiment folder would be there. It would by default be known as 0. Yeah, you can run it inside.
Yeah, you can do it inside Anaconda. Cool. We'll actually start moving on. We still have quite a bit to cover, but we'll keep taking your questions, right? So, right. We'll start with a basic regression example, and we'll first execute the first set of cells, which are basically the import statements that basically require us to execute some functionalities, right? So we basically have a regression data set downloaded from UCI repository, basically trying to predict what the miles per gallon of a vehicle would be basing on some 8 features, mostly numerical, right? And I think there are a few categorical as well. So we'll try to use those features and try to come up with a prediction as to what could be the miles per gallon for a vehicle, right? So you don't have to download anything. All of that should already be there in the folder that you've downloaded within the data section, right? And you should have it as auto MPG data. So that's good. So these are all tab separated. We'll start reading the data set. So with the first separator of new line, we basically have 2 columns, one with the features and then the other one with the name of the car, right? So we'll basically expand this further to have a column for each individual features. And then that should have a data set that basically lets us work on further, right? We're also just checking and trying to convert all of these categories into numerical. We actually have a question. Yeah, so it's optional. If you already have Anaconda installed, you could use that, or just a simple Python setup would also work. Yes, you could just run MLflow UI. Yeah.
Yeah, you can just copy this URL, paste it in your browser, and that would work. The same way we run Jupyter Notebook sometimes, localhost 4x8. So it's the same way. And
so we're not actually
sorry. In some cases, localhost doesn't always work for everyone. So you can use this URL 127.0.0.1 and the port.
Yeah, we actually skipped car name. Okay, that's figured out. Cool. So everything apart from car name, we're basically making sure that everything's numerical in nature. That's that. And we're separating the dependent and independent variables. So now we have X and Y's. Y would be just our NPG column on which we want to make the prediction on. So it's pretty basic so far, right? Anyone who has knowledge on ML should follow till here. Then we do a train test split. Then we have an evaluation function that basically returns 2 metrics, the RMSE value and the mean absolute error. You can add more if you want, and just make sure that you add them into the return statement as well. Cool. So let's first look at a conventional way, as in how one would actually work on and probably keep track of their models or the performance of a model, right? So it'll be something like this. You basically define your hyperparameters to start with. You choose a model, you put in those parameters, then you apply the fit method, then you do predict on the test set, then you'd see what the performance is like, and then you put in print statements to make sure that the readability of the code, right? You put in prints and see what's the performance of the model is like. Or if you want to save this notebook later on, you would probably put in final one, final, and so on, like we've seen in the screenshots earlier, right? Let's say if you're going one step ahead further, let's say we're doing hyperparameter tuning and we're doing it the old crude fashioned way, right? So we have basically a list of values for alpha defined, and we have a list of L1 ratios defined with a variable called L1 ratios. So we loop over each of those, and on each instance, we basically apply one parameter from one element from each of those lists and basically do a prediction, then get the evaluation metrics, and then basically print. And that's how we actually keep a track of each run that we are actually executing, right? And so this is very crude way, right? I mean, we don't know or it's actually hard to basically go back and check what was our best model, or what was the model where I was getting this RMSE and that mean square error, or what was the parameters that I used for a run where I was getting RMSE value as 3.2 or etc. Right? So now let's see how MLflow addresses that. So far so good, or do we have any questions? I don't think we have. Cool, I'll move on. Right. So using MLflow, we start with defining an experiment name. Let's call it simple or plain regression. And then we are saying create experiment. Now, the reason we have actually put it in try except statement is basically create experiment would run into exception if the experiment name is already defined, right? So just to let you know that create experiment, if you execute the same line of code again and again, you might run into exceptions. That's why we have a try except. Instead, an alternate method, we'll also discuss that, like how if an experiment is already defined, what method can you use? I'll come to it in a little bit. But yeah, that's the whole idea of using a try except here. So we have the experiment name defined. Now we are also creating an empty folder called images. If it does not exist, but if it exists, you can just skip. Right. Now we are doing MLflow.start run. So we are passing in the experiment ID, meaning every run that we do here. That's totally up to you. I mean, the way you want to organize. So you can actually make several runs with different models in your in a single experiment, or if you just want to in one experiment, if you just want to play around with one model, that could also be done. We'll actually come back to how you can better organize things, right? There are ways you could set tags, and there are ways you could actually go back and search. So we'll actually cover those. Cool. Yeah, so we are just, while we are initiating the run method, we are saying that everything that we're calling under this run should be tagged into this experiment ID. And we can also give a run name, let's say, right. Cool. So here we're actually trying to simulate the EDA process with just single line of code. We're just plotting a box plot for all the features, numerical features, right? And we are saving it to a directory that we created above, right? Images, right? And then we are calling the log artifacts method. So in the log artifacts method, you just pass in the directory, the location of that directory where you want to log it for future purposes, right? And you will see how that can be seen or accessed in the UI in a bit. But yeah, log artifacts can take in the path of the directory where everything inside that directory would be tracked for that given run that you're running. Cool. Then we have the hyperparameters defined, just playing around with some 0.02, 0.15. Then we're calling the elastic-net model with the same parameters. The rest of the code is pretty much same, right? The conventional way in which we're actually running the model. The only change that we're doing is encapsulating it with a with statement. And then whenever we are defining something and where we want to reuse or access it later on, we're just using the MLflow methods called log artifacts or log params. So log params is for the parameters. It's basically a string, a key value pair, like alpha would be the key and the value would be the string. So params requires both of these to be strings. So even though you pass in numbers, it will be stored as strings in the UI, in the tracking server, basically. Then we have log metrics. It's again, it again takes the key value pairs, keys for the metric name, and then the value would be the value itself. These are numeric. Yeah, so you can actually use MLflow.log metrics. And actually, instead of doing it multiple times, you could actually pass them as a dictionary with a key value pair, right? RMSE can then be RMSE, then MAE, you could also do the same for log params as well. Cool. And then lastly, we got whatever model that we've built, right? We're using the sklearn flavor that we were all talking about so till now, and basically helps us in deploying this model in a platform agnostic way, right? So we're basically logging the model with the flavor called sklearn, and then calling the log model method and saying what model, the object of the model that has to be passed in, and then some name that you want to call this model or refer to the model later on. So executing this cell should not take much time. You should see a plot, and that means the execution is done. For visualization purposes, that you can also rerun the same cell with multiple values of alpha and L1 ratio, right? So that will basically keep logging it and see how that looks in the UI later on. I'm just putting random numbers here. Yeah. Cool. I did 3. You can also do 1 or 2 or 3 or whatever you prefer. But yeah, I hope no one actually faced any challenge in executing that cell. Looks like we're good. Cool. Right. We'll actually go back to the UI and see how that looks. So if you go to the UI and do a quick refresh, you should see an experiment called plane regression, right? And within regression, you should see a table that basically contains all the runs. So right now we actually ran several runs, right, with the name run 1. So we have 3 here that have been populated. We'll just look at what all attributes are covered here. Then we'll try to see what each of those individual runs have in more detail. So user would be the username from which this particular code was executed. Source is right now a location from the local directory. But let's say if you're running something from Git or another repo, you could see that location or that source here. And if you're using Git or any other version management, you'll see the version for that code as well. Right. So we actually used a method called log model in the end. So if that's the case, we're actually saving some model, right? So if if we actually did that in your code, you should see the flavor with which the model was logged here in the model section. Then if we move further, you will see a few set of columns for metrics and parameters. So metrics is what was the performance on the test set after each run. Both MAE and RMSE can be seen. You can sort them using the column. Then if you move further, you will also see the alpha and L1 ratios that we have actually set for each run, right? Cool. So now what we'll actually do is go back into one of these runs. You can click on the column within start time. That should open up a page that is different, but has more details into the run that you actually clicked on. So Tom, you're seeing only one run because you executed that code only once. So if you try repeating that by changing some parameters, you should see more getting logged. If you don't see it even after that, just try refreshing the page. You should see the updated results. How do we run the UI? So we've actually discussed that. You open up your command prompt or terminal if you're on a Linux machine. You go to the project folder, wherever you have your notebooks, and you click and you just type MLflow UI. And this is an optional parameter, the port, if you want to open it up in a specifically different port. So we generally only have flavor as sklearn because that was the model that we have built with, right? So we were actually importing Elastic Net model through the sklearn package, right? Cool. Okay, going back. So we now are in a detailed page for a given run. So we have a date and time for which it was run. We have the duration, we have the status of it finished. And if for some reason your code didn't execute, you will see some different kind of status, right? You'll see if it's in process, if it's in progress, you will see something like in process. But if it probably ran into an exception, you should see unfinished and so on. Does MLflow take care of requirements of TXT? Yes, it does take care of requirements of TXT. We'll just get to that in a bit. So we again see the alpha, the parameters were here, the metrics here, and some tags which we haven't actually put in through the command, but later on, let's say if you want to put something, some tag, I don't know, developer, you can just then you should see these tags again appearing in the original page of the UI, the landing page. Cool. So now coming to artifacts, right? We've actually developed a plot that we were actually trying to visualize, right? And that gets logged, and that can be visualized through the artifact section. You can zoom in, zoom out, and any operation that you want to do. This gets tracked with the run that we have actually run. So coming to the requirements txt, so when we've actually logged the model, it takes care of what all models are required for it to execute properly, and that gets tracked with the requirements.txt. Similarly, we have the conda YAML file that basically gives the requirements for you to set up an environment and get started for replicating this particular project. Then we have ML model file that basically contains the details of the model, right? And that so we have the flavors. So Python function would be by default because our language for choice for Python function. Then we have the flavor called sklearn because we're actually using the sklearn package to build a model. And then we have the pickle file for that model. It's called model.pkl. Then we have the sklearn version logged in. We have the Python version logged in. Then we have the run ID through which this particular model was logged. So going back here, you should, if you refresh, you should now see a column for tag if you guys have developed some, if you guys have added anything there. Okay, I'll just go back to questions.
Can we start with a question from Hong Pai? I'm sorry if I'm pronouncing it incorrectly. The run name column is all empty. Am I missing any steps?
Okay, can you just do refresh here? That should load up if a run has been tracked. If you still don't see it, that means you have opened the tracking UI from a different directory where the ML runs folder does not exist. So the key to have this data seen in the tracking UI is to have this folder called ML runs, which basically has the run details.
starting the MLflow run, you have that code with MLflow.start_run. You have mentioned the run name there. If run name is not mentioned there, that might be the reason your run name column could also be empty. Awesome.
Run name column is empty. My bad. Okay, cool. That's fine.
Can you also see the data version used to train this result? If you log that, that would be visible. Maybe we can log that, Kalyan.
Yeah, we'll actually do that in the next example. I'll actually come to that in a bit.
Awesome. Rahman asks, how is the pickling done? We are using log model.pickle. We are not using joblib, we are using a pickle.
Yeah, we are using pickle. So it's automatically done, but yeah, it's the pickle model. Yeah, sorry, go ahead.
Sorry. Brian wants to ask, for nested loops, we are doing it twice. Is there a smoother way? Yes, with MLflow start run, you can put nested equals to true. That's an optional argument. If you do that, then multiple runs would be recorded in the same start experiment run. And I've also pasted the steps to launch the UI in case someone wants to refer to them again. Perfect. Tom says he ran the cell in Notebook multiple times, refreshed it in dashboard, and I still only see the original run. Okay. A good way to check this would be, can you navigate in your file explorer or however system you're using, Mac?
Yeah,
can you navigate to the file explorer and show ML runs and see how many run experiments are being logged? In the same experiment under Hello World, you can probably have multiple runs, so you should be able to see those. That could be a good checking point.
Yeah. I'll just take one more question around grid search, I think. Yeah, there's definitely a smoother way to do hyperparameter search, right? You could use a grid search or a random search. We thought we'll actually keep it as a takeaway exercise and ask you to use another method of MLflow that basically lets you log automatically. We'll come to that in a bit, but that's certainly doable. To keep things simpler, that was the approach that we've taken, but you could definitely do that. So the YAML files are basically in the model folder. The folder should be with the name with which you have saved the model. So if you have logged the model, then only then you will see these YAML files. Right. Cool.
Awesome. We are good to proceed.
Awesome. We'll just go back and we'll just open the classification example. Again, the data set is pretty basic, a toy data set, again on cars, but it's a classification problem. And we're trying to evaluate a car in 4 different categories, whether it's acceptable, unacceptable, good, and very good. Using various features like what's the price, what's the maintenance cost, what's the comfort, very basic stuff, right? So we'll again go back to the notebook, import statements. We are basically importing a dictionary classifier, and we're also using one hot encoders to encode these categorical features, right? Then a similar method of reading this data, which is tab separated into data frames. And then we are also splitting the dependent and independent variables into X and Y. Then we have a train test split method called in, so to split the data set into train and test sets, right? So most of this is same. I'll not repeat. We're defining an experiment name, and that's it. So in this particular example, what we're trying to do a little differently is basically show you how tags can work and how you can tag a particular run that you are initiating. And then so let's say after pre-processing or after feature engineering, you want to keep a copy of your data, right? So in this case, what we're actually doing is we're encoding the data, and then we're keeping a copy of it into the data processed folder, and then calling the log artifacts method on it, so that this gets logged to the run that we've just initiated. So, right. We again start with the start run method, giving the experiment name, the run name, which is optional and can be, which is optional. If you don't put anything, it'll be a blank in the column in the UI. Then you can set tags, right, to organize your experiments or runs for later purposes, right? So, and the way to do it is called the set tag method. If it's a single tag, you can pass in the key value as two arguments, both strings. Or if it's multiple, you can just pass in a dictionary with the key value pair, right? Then we're just using the one hot encoder. We discussed, we've encoding it on the training test set. Then we are saving it to a CSV file, and then we are logging it in as an artifact into the data processed folder. Right. The next bit is pretty common. The conventional approach, I would say. You define some parameters. The max depth is 5. The maximum features is 15. And you initiate the classifier. You call the filter method. There's one cool thing that we've actually did, and we'll actually show you how that looks in the UI. But we've actually used a package called SHAP that basically brings in interpretability to the model that you're building, right? So SHAP, the whole idea of putting it here is to basically showcase that MLflow can work with several libraries just out of the box. You don't have to do anything, and not just with the code. You can integrate it with the other components like the UI and so on. So we'll just come to that. For time being, we've actually commented out this code because it takes a good 10-15 minutes to bring in that explainability. But what it does is basically uses game theory and the math behind it to bring in that explainability. So it could actually be a whole different session to talk about. But for now, we'll just keep things simple. And what we're actually looking is how a different package can work in and can be integrated with MLflow runs and how it works with the different components, basically. Then we're using a predict function on the test set, and we're just computing a simple accuracy on the test set. Then we are just logging the parameters and the metrics like we've seen before. And we're also logging the model using the sklearn flavor. So you can run the cell a few times. And in the end, we've also mentioned some classes, right? The acceptable, good, and acceptable and very good are the classes. Right, so if you go back to experiments and go to simple classification, I ran it twice and I have 2 runs here, right? And the accuracy is 81%. We see the same details, the run name and everything. But if we go further to the right, we see the different parameters of this model, right? The max depth, the max features, and the tags that we have set, whether what's the problem type, what's the description, and what's the model type. Right. Cool. If we go into the individual runs, it's pretty much the same stuff. Going into the artifacts which are logged here, so you'll see this encoded version of the data set, both the training test sets. So sort of keeping a copy of the data that you have used with some pre-processing or after some imputations, right? Right, then we have the model. Again, we see it here because we have logged the model, the same stuff, the ML model file, the conda, the pickle file, and the requirements.txt. I'll actually go back and showcase you the run where we've actually called in the SHAP module and tried to bring in some interpretability, right?
Classification.
Yeah, right. So by default, so the thing that SHAP would do is basically generate some output and basically log it as artifacts again. So all of that is automatically done with just a single line of code. And what it would log is basically an a chart that basically explains the feature importance for the different classes. And then it also has these base and chap values, which again could be analyzed further with the NumPy package and can also be used for plotting purposes. Yeah, so if you just run the code with uncommenting, you will see an error saying no module named chap. You'll have to install it separately, but it will take a good amount of time. So that's the reason we've actually not mentioned it as a prerequisite as well. But yeah, the whole point being how it integrates well with the MLflow module in general. So this is a toy data set, right, with very small set of features, and it took us like 12 minutes to do that. So if the data set gets bigger, it'll obviously increase the time. Yeah, so the way to compare all metrics, one way to do it is through this experiment page. One feature that we could use is basically if we go to the regression experiment, and let's say we want all the runs filtered with metrics.mae value being less than, I don't know, 2.4. If there are any, they're not. Right, typo there. So metrics.mae and get all the values which are less than 2.5. And that should give me a filtered view of the runs which have this particular performance on the model. You could also sort and filter, or you could also change the columns if you think something's unnecessary to visualize or see. We'll also see a small demo on how you could actually filter through runs and use them. How you can filter through runs in a programmatic way. So we'll just quickly jump there, keeping the amount of time we have left in mind. And that should be in the search runs and model serve notebook. So for searching runs, we again start with importing two packages, MLflow and data frame. So MLflow has a method called search runs, which basically takes in the first argument being a list of experiment IDs that you want to search on. So again, experiment IDs are stored as strings. So we just pass in a single string with say 0. And that would basically return me a data frame containing all the run IDs, which you basically see in the UI here. Right. So experiment 0 for me is the plain regression experiment that I did. And I see all the runs that I have here in the notebook. Right. Then you could also pass in some queries or search strings. Like you want runs which have an RMSE score of less than 3.27 and the mean absolute error being less than 2.45. If you do that, you will see a smaller section of the data frame being returned. Right. You could also apply in the search strings that you pass in, you could also put in additional arguments on the tags which you want to filter, or the parameters of the element ratio or alpha, or limit something to a particular day of the experiment, and so on. Cool. So like I said, it returns a data frame. So you could actually copy everything to a data frame and then do some of your operations, like how I'm doing here. I'm trying to filter out runs which have the minimum mean MAE value, right? And for me, it's this run, and it returns the ID here. Right. So let's say I don't have all the details of this run ID handy, or I'm too lazy to actually browse through the data frame here. So what I do is actually copy this ID and paste it here. So to get the details of the run, you basically initiate a MLflow client. And after you do that, you use the get run method on the client to basically get all the details here. Another way to sort of visualize if you don't like the UI in any case. But yeah, that's another way to do it. No, search runs you should pass in the experiment ID as a list, and the ID being a number. ID being a number, but passed in as a string. So Here we're just seeing a simple approach of serving a model, and we are trying to deploy it as an API endpoint, right? So what we do is basically pass in this command into the terminal window or your command prompt. So we are calling the MLflow CLI API and then saying models and call the serve method. And we're giving the model URI. So model URI is basically that unique path for which, for the model where we have the .pkl model saved, right? And if you recall, we have saved all our pkl files for the regression problem with this name, plain regression underscore model. And it is there in the artifacts folder. If I can go back. ML runs 0. And should be here. Right. So we have a plain regression model, and this is what we're trying to invoke basically from this method. And we can again set a port by default, which will act as where it will take in the requests at this port, right? So I'll just copy this command, open up a new terminal window, right? Try to zoom in a little and just paste this here, right? Oh, no. Okay, just give me a second. Yeah, I think it's an issue with the path. Yeah, that's what I'm trying to set.
Kalyan, maybe we can go to the UI, get the model path from there.
Yep, I could do that. Just give me a sec. Okay, we have it running. So yeah, I actually did I rushed into things, but what you actually have to do is basically change the directory to the ML runs and then, call this MLflow serve method. So yeah, I basically changed the directory to where I have the notebooks, and then I'm just calling this MLflow serve. And then that would basically, set up a listener at this port for some requests. And the way to actually send a request and get some predictions is basically use a curl method, and then you pass in your local IP, the port, the same port with which you created the server, pass in that, and add a keyword called invocations. And the content type can have several options, like JSON and so on. We're sticking to JSON here, and it's structured in a way that we first pass in the columns and define them and what's the value for those columns are, and those are mentioned with the value with the key called data. So if I just execute this, this should return me a value for this prediction. I understand. So that's something that anyway everyone has to do, because the IDs are always unique to your runs that the runs that you initiate basically. So yeah, that's about model serving. We'll actually take a take a pause. If you have some questions, we can take those.
So data folder is already included. Yeah.
So data folder basically contains the input data that we've been using from the UCI repo. So that's already included in the Google Drive folder. So Databricks had good question. Databricks has a managed version of MLflow that basically lets some of these configurations already predefined, and it's easier to get started on. Yeah, but it's at the core of it, it's all the same. Managed MLflow just adds a few more features that makes working with MLflow more seamless and enjoyable, I'd say. Thank you, Yang. Thank you, Rahman.
Thanks, everyone. Before we close up today's session, we'll just demonstrate. You can follow along with the notebooks later. The reproducibility using a GitHub repo. So sometimes you want to look at those modules. So Kalyan, can you touch base on that? And then we'll conclude the session.
Okay. Yeah, so ML projects, right? So let's say you want to reproduce one of your team members' work. And the way you can do it is actually use ML projects. So what I'm trying to do here, let's say my colleague has a project hosted in GitHub. And the only requirement here is to basically have an ML project file. Again, it's a YAML format file that basically contains entry points and the parameters that the main function actually takes in. And the command basically mentions how you take that, or how do you call that script or function? How do you initiate it basically? So it's a simple train.py file that basically tries to get some predictions on wine data set. It's very similar to what we have tried to execute here. But the cool thing that I want to show here is basically you start with set experiment, you define an experiment name, and you just use the URL of that Git repo, right? That basically should contain the ML project file. Then you pass in as an argument into the MLflow.run method. And then the parameters that the script takes, the alpha and L1 ratio, for example. So if you just do run, it'll automatically take care of the requirements.txt, the conda setup, and so on. And then just run this, and you should again see it in the tracking server, in your own tracking UI, basically. So it's here, the one that we just did 17 seconds ago. We know where we run it from. We have all the parameters and metrics. We also have the artifacts, just the model, because we're logging your model. But yeah, that's one thing that I wanted to show. So you don't have to worry about setting up everything on your machine if you want to replicate someone else's. You also have the source. So if you just click on it, it should take you to the GitHub repo. You'll have the version with which it was running, and so on. That's the whole idea of using projects. You can easily collaborate and just pick up from one of your colleagues' work and just continue from there on, if the ML project's YAML file is defined. Yeah, just to summarize, I'll just take one more minute. I know we're already over time. So DevOps is basically a new field. It's basically machine learning plus the operationalization or productionization of these models. So they're really exciting, but it also comes up with a lot of pain areas and challenges, right? And we feel MLflow is like a very good open source tool that integrates well with a lot of these packages and modules and lets you collaborate even further. So just doing a quick recap of the 3 key components that basically facilitate us in all these actions. The tracking, you can easily visualize and track your experiments and runs and filter them out, pick up the best run, then use that run, replicate it, and package and and package that model and in a platform agnostic way. And if you want to just transfer your project to someone else, make use of ML projects, and with the YAML file, anyone should be good to just start working on it. just one takeaway exercise if everyone's interested to just continue where we're left off. So one cool feature is the auto log method that basically, right now we were all logging the parameters manually, right, after each invocation. So sklearn primarily and a lot of these common libraries have the auto log functionality through MLflow. So MLflow would automatically take care of logging these parameters and metrics for each run that you do. So we highly recommend using that. We have some sample data sets. All of them are classification if you just want to play around, or if you have any deep learning example, then explore the TensorFlow and Keras methods. You're always welcome to do that. But yeah, make sure to use the log artifacts method and log models to, all these different stages of the ML lifecycle, and let us know what you feel about and what your thoughts are after using this package.
Awesome.
Yeah, cool.
No, sorry. You finished with the reference?
Yeah, I just wanted to highlight some references that we found really interesting and useful. We'll just leave them with the presentation, but yeah, and you guys should be able to access them. All good.
Awesome. Time is over. And yeah, the presentation was amazing. I think the people was really happy, was really well presented. And again, we want to thank you both for the great presentation and for being part of PyData Global 2021. Thank you very, very much.
Thank you, Kevin.
Thank you.
For the team. And thanks everyone for joining.